All right, let's dive into something that feels straight out of science fiction. Can we actually create life inside a computer? I'm not talking about just a simulation, but a whole digital universe where complex, evolving beings just emerge and thrive all on their own. Let's see just how close we are to making that a reality.
And that's the big question, right? Can we kickstart a process that just spontaneously keeps generating more and more complex, more and more diverse forms of life forever? With no end in sight? It sounds totally wild, but it's a very real and super active area of research.
So there's a technical term for this. It's called open-endedness. And the key here, the really important part, is that the complexity isn't pre-programmed. It isn't engineered. Instead, it just bubbles up from the bottom, emerging from the system's own internal dynamics. So how on earth do you even start to build something that can build itself?
Okay, so where do we even begin? Well, we start small, like really small. Our journey begins in a kind of digital petri dish, a world built not of atoms but of pixels. Welcome to a world called Lenia. I want you to imagine a huge grid where every single pixel, every cell, follows a very, very simple set of instructions. There's no master plan, no central computer calling the shots. It's just millions of individual cells, each doing its own thing based on the same local rules. And from that simplicity, something truly amazing happens.
And the rules that run this world are just shockingly simple. Each cell just looks at the pixels right next to it, uses a quick math formula to decide if it should get stronger or weaker, and then it updates itself. That's it. A simple three-step loop happening over and over, all across the entire grid, all at once.
And here's where the magic happens. This is the power of emergence. Out of that simple three-step rule, these complex, stable patterns just appear. And they look like tiny digital organisms. They move with a sense of purpose, they hold their shape, and they can even navigate around obstacles, almost like they can see and react to the world around them.
Okay, so we've got these single creatures. That's cool, but life isn't about just one organism, right? It's about ecosystems. So what happens when you introduce a little competition and maybe some cooperation? Let's scale up and find out. So to dig into this, researchers built a new playground, basically. It's called Flowlenia. And in this world, they could throw in a bunch of different species of these patterns, each one with slightly different rules, and just let them interact in the same space, all competing for digital mass, which you can think of as resources.
And what they witnessed was just mind-blowing. A completely unscripted evolutionary story played out right before their eyes. It started with just a random mix of species. Pretty soon, they were competing for resources. But then, something incredible happened. Some of these species started working together, forming these more complex, symbiotic life forms that were way more successful. And these new forms, they just thrived and spread everywhere. Now, this is the part that you really have to let sink in. Nobody programmed evolution into the system. There was no survival of the fittest code running in the background. Evolution just emerged. It happened naturally, purely from the physics and the interactions within the system. It was a true bottom-up process.
So it's worth taking a step back here to understand the philosophy behind this. The Lenia world operates under what's called an enactivist framework. The thinking isn't in a brain, it's spread across the creature's entire body and its interactions with the world. But to explore more complex stuff like curiosity and decision-making, the research shifts to a more familiar mechanistic framework, where we have agents with distinct brains, sensors, and bodies.
All right, so let's shift gears. Let's leave the primordial ooze of Lenia behind for a moment and focus on individual embodied agents that can actually learn and make their own decisions during their lifetime.
Now, usually, when you want to teach an AI something, you use what's called reinforcement learning, or RL. It's pretty simple. You give the agent a goal, and then you give it a reward every time it gets closer to that goal. It's really powerful, but the catch is, it always relies on a human programmer deciding what's good.
But here's a wild idea. What if the agents could come up with their own goals? This is called autotelic learning. Instead of chasing rewards that a human gives them, these agents are driven by their own internal motivation, something like curiosity, to just go out and explore and learn for the sake of learning. This is way closer to how we see animals and, humans learning grow.
Okay, so now we have these individual agents that can learn for themselves. What's the next logical step? You put them together, of course. Let's see if they can build a society.
And what's so important to understand is that these agents, they aren't just floating around in their world. No, they're actively changing their environment. Biologists call this niche construction. And by doing this, they create totally new challenges and new opportunities, not just for themselves, but for everyone else around them.
And this led to something that, honestly, it's just unbelievable. The emergence of digital agriculture. Get this. The agents figured out that by acting in certain ways, they could actually cultivate their food source, making it more abundant and sustainable. They literally learned how to farm.
But you can probably guess, this creates a classic social dilemma. If everyone has access to these farmed resources, what stops them from just taking too much and destroying the resource for everybody? This is the famous tragedy of the commons. If they were going to survive, they had to learn how to cooperate. And incredibly, they did. They figured it out, and they did it through a key psychological mechanism called shared intentionality. The agents learned to communicate, to line up their personal goals, and form a shared goal that they could all work towards together. They evolved from just individual farmers into a cooperative society.
All right, so let's zoom out. We've gone from a single pixel to a full-blown digital society. What's the big takeaway here? What does all of this mean for the future of AI and even our own understanding of life?
Well, first off, we've seen that you don't need to program evolution. It can just happen, bubbling up from simple physical interactions. We've also learned that pure curiosity can push agents to learn way better than just chasing external rewards. And we've watched cooperation evolve as a real solution to tough social problems. You know, maybe the biggest lesson here is that instead of trying to engineer intelligence from the top down, maybe it's better to just search for the right conditions and let intelligence emerge on its own.
And that right there is why this research is such a huge deal. This whole bottom-up approach could completely change how we build intelligent systems. Think about it. Instead of brittle, single-task AI, we could create more general, more adaptive agents. It could inspire totally new ways to design robots, and maybe most profoundly, it gives us a powerful new tool to study how life itself might have gotten started here on Earth. So I'll leave you with this final kind of mind-bending thought. If complex, learning, cooperative life can emerge from something as ridiculously simple as a pixel following a rule, then maybe the true building blocks of life aren't just molecules, but the fundamental principles of self-organization and emergence themselves.